Good. So someone has a bunch of messages here. Let's see here. The question: will you post the updated schedule? Oh, are you Valerie? You're talking about the syllabus. Valerie asking me if I'm going to, okay. Yes, it's already there, by the way. It's already, I believe I already posted there, version number 3. Okay. Double check that for me. I believe they already uploaded it there. If I didn't, let me know and I will do that. Okay, I'm not sharing the screen. Let me see. No, I'm sharing the screen. Right. Can you see my screen, Ramon?
I can't see the screen you're supposed to be sharing.
You cannot. Let me see. Let me stop sharing here in my computer, and then I'm going to start sharing again. Let's see. Screen 1. What about now?
Yes.
Okay, good. So, and everybody else, okay, this is screen number 1. So that I'm going to, scroll up and down the notes. Right? Can you see me scrolling up and down the notes? Okay.
Yes, I can.
You see, Valerie, you see only version 2 of the syllabus on Canvas, right? So let's see here. Canvas. Let me go there to the physics 2025, right in here. Let's see. Oh, yeah, you're right. I didn't upload it. Okay. Okay, let me upload that now. So syllabus. I created the PDF version of the syllabus, but I didn't upload it. Okay, so let's do that. Let's fix that. Files. Drop it. Right, going back to home and file version number 3. Right in here, add item. And now we don't need this one anymore. Remove. Okay. Okay, so let's see. Okay, now we have version number 3 there. More students are trying to add. Let's see. And I can see. Side note, are you going to take attendance now? No, I didn't take attendance yet. Hello, did you take attendance? Ever joined the class? Okay, good. I didn't take attendance yet. I usually take attendance just before the break. Okay, so I give time for you folks to join us. The notes is here too, right? And I already posted the second class meeting, right? The first meeting, we didn't have anything important to record, so there is no need to post it. But today's I'm recording the class right now. Share, okay, and going back to so going back here to the notes. Can you remember that? Okay. Again, you don't have to memorize those exact numbers, but you have to know that the electron is the least massive of the 3, proton is the next one, and the neutron is the heaviest of all. And what else you have to know? You have to know that the masses of the proton and neutron is roughly, right? 1,800 times more than the mass of the neutron. A number that's easier to memorize is 2,000 times, right? If you use 2,000 times, you'll be incurring a mistake in an error of 10%. But the more precise number is this one. It's not exactly 1,800, okay? But it's close enough. Let's see here. Thank you. Now, what we have been covering, summary of what we have covered so far is the electric charge property, is a basic quantity of matter. And we talked about the electric force. We talked about electric materials. There are, the most important are those two, conductors and insulators. There are two others that we don't cover in this course. There are two more that which are not covered in this course, and the other two are semiconductors and superconductors. In reality, there are four electrical materials, but you have to concentrate on those two. And now we're going to talk about the electric field. Okay? The mechanical counterpart of the electric field is the acceleration of gravity. Okay? The acceleration of gravity is the mechanical counterpart of the electric field. We can also call it, which is also called the gravitational field. Gravitational field. And let's see how the electric field works more or less just like the acceleration of gravity. It works just like the acceleration of gravity. Okay, so let's take a look at the equations of the gravitational force that you saw before for a mass, right? Nearby the surface of the Earth, nearby the surface of the Earth. You already know that the force in an object is, here you go, the gravitational force, the weight, right? The weight or the gravitational force is equal to the mass of the object times the acceleration of gravity, mg. And it points towards the center of the Earth. If you go ahead, divide the force by the mass, right, on both sides, what you're going to get an equation, the equation for the acceleration of gravity. Okay, which is, like I mentioned to you, which is also called the gravitational field. Note that the acceleration of gravity is the force divided by the mass. And by the way, the mass is the source of the force, the source of the gravitational field. This mass should be the mass of the mass of the object that's subject to the gravitational force of the Earth. Okay. Note that the gravitational field is the force divided by the source of the field, which is the mass. Okay? That's one equation for the gravitational field. That's the equation of the gravitational field nearby the surface of the Earth. However, far away from the surface of the Earth, the equation is a little bit more complicated. The equation for the force, right, and is given by the universal law of gravity. Remember that? So now I'm going to, instead of using the W, right? I'm going to use F, which, by the way, I'm going to put like that. The weight is force of gravity, and I'm going to put a subscript here, G. I'm going to put a capital G. Okay. So if you have two masses, separated by a distance r, this force is given by big G m1 m2 divided by r squared. Remember that? That's from physics 6, the previous course in physics. Suppose that m1 is much bigger than m2, right? So here you go, m1, let's say, is the Earth, m2 is the apple, right? Say, let us say m1 is the Earth and m2 is the apple, Newton's apple. Newton's apple. It's supposed to be 2 here. Therefore, then we say that the gravitational field of the Earth, right, is given by the gravitational force applied to the apple divided by the mass of the apple. And I'm going to divide by the mass of the apple here as well. When we do the mass, m2 is no longer, m2 cancels out here. And the gravitational field, or the acceleration of gravity, due to the Earth, is given by this equation, where r is the distance from the center of the Earth. In the above, r is the distance from the center of the Earth. Okay, I'm going to write it here. The gravitational field, lowercase g, going to be like that. The gravitational field depends on the mass of the object, which in this case is going to be the Earth, the mass of the Earth. We have a similar situation for the electric field. Okay. Now remember that the force between two charges, and I'm going to put like that. Force between charge 1 and 2, right? Electric force is going to be, and that you have memorized, right? K is a very similar equation, but it's not exactly the same. Charge of 1, charge of 2, divided by the distance of them. Not much different from the previous one, right? So just like before, now suppose that Q1 is much greater than Q2. Okay. Then we say that the electric field of Q1 is given by, what's going to be the electric field of Q1? Is going to be given by, here you go, by the force divided by the other smaller charge. Okay, it's going to be something like that. Okay, here we have the force divided by the mass, where the mass is the source of the gravitational field. Here we have the force divided by the charge, whereas the charge is the source of the gravitational field. Okay, so it's force divided by the source. For the mass, for the gravitational force, the mass is the source of the gravitational field. For the electric force, the charge is the source of the electric field. And now we have this equation here. That's for the point charge. Okay. And I can write here. We usually denote the electric field by the letter E. And because it's the electric field only of the first charge, we denote it as E sub 1. Okay. And electric field of charge 1. And there is a more intuitive way of understanding that as well. Let's take a look. Okay, so you have here an electric charge. Let's say electric charge 1. It's there in space. And then I'm going to put the x-axis and the y-axis, referential, right? Coordinate system, our coordinate system. And then suppose that we want to map the electric field of this charge. What do? We go ahead and place another charge, another point charge in the surroundings of this charge. And by the way, very important, this charge is supposed to be much smaller than big Q1. Okay, that's the condition to determine the electric field of the other charge. This charge here, and it has to be positive, by the way. QT, has to be greater than 0. What does it mean? It means that in order to find out the electric field of a given charge, we have to use a test charge that's positive. QT stands for test charge. That's positive, and then from then on, we can map the electric field of the main charge. Okay. So how do we do next? Okay. Put this test charge nearby at a given position, right? The distance between this charge and this charge is the distance r. And then what do we do next? We find what is the force that the main charge is applying to the test charge. The force is going to be repulsive, right? And then what do we do next? Here you go. Here's the vector position. We already, what did I do here? Yeah, okay. Vector position, I'm kind of repeating it. Here you go. We eliminate the test charge from that original place. That's what it means. That's the distance to the test charge. The force will become 0. But something else will be left behind. Okay? And this something else that left behind is going to be the electric field. Okay? The force is not there anymore, but the electric field remains that all the time. It's just like the gravitational acceleration. The gravitational acceleration is everywhere in the surface of the Earth, whether you have a mass there or not. Okay, the electric field too. And here we are mapping the electric field around this charge. Okay, notice that I put a dashed charge here to denote that the charge is no longer there. Okay, so I'm going to, if I want to know the electric field elsewhere, I put the same test charge elsewhere. Get the electric force, remove the test charge, and we know what is the direction of the electric field, and so on. We repeat this procedure over and over again, right? Third charge, fourth charge, and here you go. That's the electric field surrounding the main charge at those specific points. That's how we find out the electric field. Did you get the idea of the electric field? The electric field has the same direction as the electric force applied to a positive test charge. Okay, there is more. As we get closer and closer to the main charge, the electric field increases. That's what we have here for E4. Here's the electric field at this point, the electric field at this point, electric field at this point, electric field vector at this point. It's very important that you have this, that you visualize the electric field in this way. It's very important because it's going to help you understand some other things that are going to come along later on. The electric field is something that's invisible to the eye, right? That's why we represent it as an arrow. This arrow representation helps you see something that is invisible. And in a way, it's very difficult to visualize any other electrical phenomenon if you do not have this picture in your mind. That is the electric field distribution for a point charge. Going back here to my notes, right? Here you go. This equation here, if we put it in terms of vector representation, vectorial representation, it is going to look just like that, right? Here you go, vector. And I have to represent the radial vector, the unit radial vector, from the origin, from the position where the main charge is. In the above, the unit vector r hat, okay, is the vector that points from the position where the main charge is located to the position in space where you want to know the electric field. That's what we have here. Okay. Let's see. Now, oh, here's the mass, right? Now we are doing the same thing for the mass. x-axis, y-axis. We're going to repeat exactly what we did before. And here you go, the test mass, the apple. The test mass is the apple. Or any other object is a very small mass. Determine, you go here, we have the vector position of the test mass from the center of the main mass to the center of the test mass. We determine the gravitational force, apply it to the test mass. We remove the test mass, the force becomes 0, but then there is something else left in there, and the something else left in there is the gravitational field, or the acceleration of gravity. Okay. Here you go, gravitational field or the acceleration of gravity. Oh, what's going on? Okay, here's the vectorial representation of the field, right? From the point for the point mass that you already saw. And here is the gravitational, is the representation of the gravitational field nearby the Earth's surface. Nearby the Earth's surface, the gravitational field is uniform, right? But as we move further and further away from the Earth, we find out that the gravitational field is not quite uniform. It's something else. Right, here you go. We have something similar for a uniform electric field, by the way. It is possible that by the same token that we do have a uniform gravitational field nearby the Earth's surface, we can also, there's a way to generate a uniform electric field with a proper distribution of electric charges, okay? And I'm going to show you later on how to do that, how we do that. But before we do that, let me show you another representation of the electric field. A much simpler way of drawing the electric field. Okay, so here you go. That's what we call the electric field lines of a point charge. The electric field lines of a point charge, of a single point charge, are represented by those lines of the electric field radiating away from the charge, from the main charge. So in order, instead of keep on drawing a bunch of electric field vectors around this charge, which is a lot of work, people figure out an easier way of representing this same electric field. And this representation is given by what we call the electric field line. Okay, so let's document things now, so you don't get lost. Going back to the notes. Okay. One way to represent this electric field in a graphical sense, graphical sense, which is easier to memorize, right? Pictures are much easier to memorize than letters, right? A picture is worth 1,000 words. Is by drawing a bunch of electric vectors surrounding the charge distribution. Okay? And we did that, for a point charge. Point charge, here you go. And here you go, the representation is right here. It would be better if you switch places here. Here you go, here's the vectorial representation of a point charge. Vectorial representation of the electric field of a point charge vector. Oh, let's see, I gotta change here, times, New Roman, okay. Vectorial representation of the E field a point charge, like that. That's like that. Here you go. Squeeze it. And then the next one, this same point charge, the electric field of the same point charge can be represented by lines. Line representation of the field of a point charge, pointing away. And you have to know how to interpret that too, right? Here, the strength of the electric field is represented by the length of the arrow, right? Okay, so here you go. A point charge. In this case, the strength of the electric field is represented by the length of the arrow. A bunch of vectors, right? A vector surrounding the electric field vectors. Vectors surrounding the main charge. We did that for a point charge. In this case, the strength of the electric field is represented by the length of the arrow. And another way to represent this electric field graphically, let's put graphically, sounds better. Is by drawing a bunch of lines centered at the charge, right? The electric field lines we also did that for a point charge. Now, in this case, the strength of the electric field is represented not by the length of the arrow, not by the length of the arrow, because there's only lines of electric field there, but by the distance between the electric field lines. Okay, so going back here. See here at this point here in this region, the distances of the closer the distance of those lines, the more intense the field is. The further the distance is from the line, oh, we should look at this one. The further is the distance from the lines, the weaker the field becomes. So the strength of the electric field is determined by the density of lines, okay? In this region, the field is stronger. In this region, the field is weaker because the density of the line is smaller. The density or the spacing, right? By the, let's put, but by the density of lines or their spacing between them of the electric field lines of the electric field lines, or the spacing between the electric field lines. Two important representations Constant K. Oh, yeah, that's right. I forgot. Let's go get the value of the K, right? The K, you don't have to memorize, like I said, but let's see. Just remember that it's a big number compared to the big G. Let's see where it is. Oh, right in here. It's a big number, right? Compared to big G. And 9 here, 9 here. It's not difficult to memorize, right? It's the number 9 multiplied by the power of 10 raised to the number 9. It's not difficult to memorize that. The unit can be easily memorized too if you look at the equation right in here. It has to be Newton. You have to do dimensional analysis, right? It has to be Newton, meter square, because the Newton must cancel, divided by Coulomb square. And that's what we have there. Yeah, meter square divided by Coulomb square. I'm gonna put this K right in here. Where? Here you go. You're welcome, Valerie. Okay, so you learned how the electric field lines field vectors and lines, right? And lines look like around a positive point charge. Okay, that's one example. We also have the vectorial representation of the electric field for a negative point charge. If we are going to put a positive test charge nearby this negative point charge, main charge, the force is going to be attractive. Consequently, the electric field is going to be towards the point charge as well. Okay. So if you were to draw the electric field vector around a negative point charge, right? Let me copy that. Let me copy that right in here. All I have to do is to invert the direction of those vectors. That's all I have to do. Do you get the idea? Let's see if you can do that for us. Size position. Let's see, maybe it's this one. No. Let's see, format. Yeah, must be this one here. Okay, and I want, let's see, this one here. And then I have to remove this one here. Yeah, let's use this one better. Yeah, that's how the electric field lines this electric field representation can be drawn in terms of this electric field lines pointing towards the negative charge. Okay, for a negative point charge, the field representation is towards the main charge. Okay. So here you go. Positive charge, field, radiates away from the charge. Negative charge field converges towards the charge. Okay? Because of that, we say that positive charges are sources of E field, of electric field. And we say that negative charges are sinks of E field. We say that the field sinks into the charge. Okay? Sink of electric field, a source of electric field. Okay? That's just for the point charge. And then we can come up with something far more complicated than that. Okay? The simplest representation of an electric field, let's say, is for a point charge. It's not just the simplest representation of an electric field, but it is the building block of a genetic electric field. Okay, so point charge, why do we study the point charge, right? So why do we study the fields of a point charge? There's a reason for that, okay? Answer. That is because the point charge is the building block of far more complicated charge distributions. Okay, that's why. That's why we study the field of a point charge. With the field of a point charge, okay, with the field of a point charge, comma, we can now find out the field of, for instance, of a dipole charge distribution. Okay? And that's what we're going to do right now. Dipole, it's not dipole the name, of let's say, for instance, of dipole is going to come later. Okay, so let's, of two positive charge distribution. Let's start with two positive charge distribution, then we talk about the dipole charge distribution. Okay, so here you go. Axis here, x-axis here, y-axis here. And I decide to put, let's say, my positive charge on the left side and my other positive charge on the right side. Both charges are positive. And let's say I want to find out the electric field here at this spot, right? In the middle line between those two charges. Because this is a middle line, the distance of this charge to this point is going to be the same as the distance of this charge to the same point. And I want to know what's going to be the net field right here. Okay? And I'm going to write that down for you here in my notes. The net field, in this case, here you go. In this case, the net field will be the not yet, Valerie. Oh, let me see. Did you mean the right to right negative charge field converge toward the charge? Yes, that's right. Let's see here. Positive yeah, that's right. I didn't. Thank you very much. Negative field, negative charge. Let's see. Oh, there's an even better way. The field of a positive charge, right, is better. Radiates away from the charge, okay? That's what I meant. Better. The field of a negative charge converges towards the charge. Okay, that's the best way of better way of putting. Okay. So going back here, in this case, the net field will be the superposition of the fields of the two charges separately. Okay. Going back here. So what we're going to do, here you go. In the next slide, here you go. The electric field of this charge here is going to point towards the right side in the diagonal direction, right? Make sense? I can even, if I did everything right, it's going to be something like that. From the center of the charge, that would be the direction of the field of this charge. Going back here. And then we repeat that for the other charge. We repeat that for the other charge. Okay. The length is going to be the length, the strength of the field is going to be the same because the charges here that have the same magnitude and their distance are the same as well. It's just the direction that's going to be different. And now we have to sum those two fields to obtain the net electric field at that point. Okay? And that's what I did here, doing the parallelogram method. Parallelogram method, no, in this case, the parallelogram method. Yeah, because here we have the parallelogram, right? Along this line here, the field points upwards along this line. Okay, so here's the electric field at this point. You want to map the electric field at another point, you go through the same procedure that we did before. First, find the field due to this charge alone, right? And because it's right at the top of this charge, it points exactly upwards. And then get the electric field contribution of the other charge. Okay? Because the distance of this charge to this point is larger than the distance of this charge to this point, the length of the arrow of this arrow here is going to be longer than the length of this other arrow, right? Okay, and then to find out the net field, we have to do the parallelogram method of the head to tail method, either way. Okay, here I'm doing the parallelogram method. The parallelogram method results in a net field like that at that point. Okay, and then you can populate all those fields at different spots, right? So at this point, right in here along this line, the electric field of both charges are going to point to the left. I just displaced the fields so so you can see this arrow. Okay, that's why I displaced the field. This charge is closer to this point, so the electric field is going to be stronger. You add them vectorially, we get something like that, and so on. I'm not going to draw the electric field lines because it's more complicated here in this case, okay? In this case, the electric field lines is more complicated. But let's see if the book has some examples, some neat examples, right? So going back here to the book, many books have let's see, electric field has the electric field of different charges distributions. Electric fields. Okay, okay. It's not a point charge, right? Let's see. Okay, here you go, 4 charges distribution. See that? There's the electric field of the 4 charge distribution at this point C. This charge is going to contribute with a field in this direction. This charge is going to contribute with a field in this direction. This charge is going to contribute with a field in this direction. And this charge here is going to cancel out the field of this other charge. And this negative charge here is going to add to the field of this other charge. Okay. And we're going to get to the parallel plate soon. Electric field lines. Okay, here you go. Point charge. Point charge that's positive, point charge that's negative. And then we're going to get to this one as well. For a parallel plate, the field is uniform. Okay, here is the electric field lines of a dipole. One positive charge, another negative charge. Okay. Do you see how the field lines are very difficult to draw? But it displays what we expect. The electric field exits, radiates away from the positive charge and points towards the negative charge, right? The fields are pointing here towards the negative charge and pointing away from the positive charge. And that's the illustration of the field, the line field. And the vectorial representation would be tangent to the field lines. Okay. Another one, that's what I did there in my PowerPoint, right? That's what I was doing. 2 charges that are positive. And if you want to know the electric field right in here between those 2 lines, those 2 charges, right? We can do that too. Okay. So here you go. Let's find out what's the electric field right in here at the origin of those 2 charges. I will copy this one and paste here. Here you go. Here is going to be the contribution of the charge in the left. And the contribution of the charge in the right is going to be exactly in the other direction. Because the distances of both charges are the same to this point, the lengths of the arrows must be the same as well. Because the lengths of the arrows are the same and those 2 vectors point in different directions, what is going to be the net field there? The net field there is going to be 0. And I will represent this net field 0 as a dot, like that. Representation of a net field 0 with a red color. Right? This red dot here represents electric field equal to 0. Net. Some points are very easy to find out the net field, okay? Other points are more difficult. Right now, we're doing just for those points that are more difficult to find, you know, we have to do the math. That we have no choice but to do the math. You may get, you know, more or less a qualitative behavior of the electric field, how like I did right in here. But if you want to know exactly, you have to do the vectorial math to get that to this point. So what, you know, if you're in the exam, for instance, I'm going to ask the fields that are simpler to find, okay? If you're doing the exam, unless, you know, there is a mathematical question. See the other one. Let's see. 2-point charge, positive and negative. The dipole is a very important charge distribution, right? Here you go. Negative and positive. We go through the same process, okay? Get the electric field that's going to be in the horizontal direction along this axis. And the electric field decreases. At this point here, this field is going to be stronger than this one, and we get this arrow, and so on. Okay, so we did lots of, and then here we have something else that's more complicated. Okay, what you saw here is the electric dipole. That's the electric dipole, one positive charge and another negative charge. And what you have here is another type of charge distribution. Okay, it's also a dipole charge, but a little bit complicated because it involves 3 different charges. The water molecule is just like that. It's just like that. Okay, it's a representation just like that. Here we have the H2O, right? Water molecule is H2O, right? So here we have the oxygen molecule and the hydrogen molecule. So they're not lined up perfectly. They are, they have this little angle here. And because of that, the water molecule is a dipole because of this representation. And because we have this, the water molecule is a dipole, it has an electric field relatively stronger compared to other molecules out there. And we gotta move on with the field as before. The net field will be the superposition of the 2 charges separately. The water molecule is an example of a dipole charge distribution. Because of that, the electric field around the molecule is relatively strong. Okay? Remember that in general, in general, that's okay. We don't have to write that down. Just keep this way. It is 10:50. Any questions about that? So that's the type of information that people talk about in chemistry, right? But do not go through the details like that I went through. There are other types of charge distributions. Here's the dipole. Here's another one that we call the quadrupole. We have the octopole and so on, but we're not going to get into that. Okay? We're not going to get into that. So let's go to our roster. Oops. Lab today is the 19th. Let's see, 12. What's that? I don't remember. Spreadsheet. Yeah, I don't remember what that was all about. Let me copy and paste elsewhere. Spreadsheet. 19th. Abir Ahmad, are you there?
Yes, I'm here.
Okay, thank you. Next is Nestor Alvarado.
Here.
Thank you, Nestor. Next is Monte.
I'm here, Professor.
Okay, thank you. Next is Justus Bowden. Are you there, Justus? Okay, make sure that you're in front of your computer. I see Justus there, but I don't hear from him, so I'm gonna put a star right in here. Let's see. Alexandra. Are you there, Alexandra?
Hey, Professor, sorry. I didn't hear you. This is for Justice right here.
Justus.
My
Okay.
apologies.
Okay, good.
Thank you.
Alexandra, welcome. Burmistrova, I see. Okay, good. Thank you. All right, yeah. Yeah, let's see. Right in there. Good. And next is gonna be Benjamin Carvajal. Hello, Benjamin. I see Benjamin there, but I don't hear from Benjamin here. Brianna Carrillo. Yep, thank you, Brianna. Next, Elizabeth Castellano.
Here.
Thank you, Elizabeth. Next is Natalia Cordoba.
Here.
Thank you. And let's see, Jacqueline Delgadillo.
Here.
Okay. Jacqueline Delgadillo. Thank you, Jacqueline. Jenny Diaz.
Here.
Okay. Next is Valerie Diaz.
Here.
Good, thank you. Juan Escalera. I don't see Juan here. Escalera, Escalera. Oh yeah, Juan Escalera is here, right? Oh yeah, good, thank you, Juan. Next is Bianca.
I'm here.
Thank you, Bianca. Wendy Garza. I don't see Wendy. Let's see. Yeah, I don't see Wendy here. So next is Dana, right? Gomez.
Yes, here.
Thank you. Edwin Gonzalez. Edwin seems to be here.
I'm here.
Okay, thank you, Edwin.
Great.
And next is going to be Eli Gonzalez.
Here.
Thank you. Next is Manuel Hernandez Pineda.
I'm right here, Professor.
Thank you. One more, Ashley. Ashley Hernandez. I don't see Ashley in my list. Next is going to be Samantha Hubert. Samantha, let's see if Samantha is here. I don't see Samantha in my list. Next, Faiz Hussein. I don't see Faiz either. Okay. CJ Joseph Hutton. I don't see CJ either. Next is Luis Leal. Luis Leal. I don't see either. Amber Lopez. Amber Lopez doesn't seem to be here either. Next, Arely Lopez. No, I don't see it. Wow, lots of people in the same row. Here you go. Genesis Lopez.
Here. I'm here.
Okay. Who is that?
It's Genesis.
Genesis, right? Okay.
Yeah.
Okay, thank you. Anybody else? Let's see. Good. Next is Mary Michaelian.
Here.
Thank you, Mary. Next, Ramon Olivares.
Here, Professor.
Thank you. One more, Taylor. Thank you. Let's see, Jeremy. Jeremy is here, right?
Yep, I'm here.
Okay, thank you. Next is Stephanie Ramos. Stephanie Ramos doesn't look like she's here. One more, let's see, Leslie Rios.
Here.
Thank you, Leslie. Jason Andres Straight.
Here.
Thank you. Candelaria Tabuhara. Okay, I don't see Candelaria here. Gema Torres Navarro. Hello, Gema. I'm gonna put a star here on Gema and
Hi,
Cindy
Professor.
Vieira.
I'm here. I couldn't unmute, but I'm right here.
Okay. Thank you. One, and next one is Cindy. Cindy Vieira. Doesn't look like Cindy here. Yeah, doesn't look like. One more. Let's see. Nuhamin Wandimu. Nuhamin is not here either. Okay, so what we have here as a total is 25. Okay, looks like there was one student who didn't answer. Maybe was Benjamin. Are you there, Benjamin? Another opportunity. What does the star mean? Is the star means that you didn't answer my call, my roll call? Okay. Okay, but now that you answered, yeah, I took out the star in the chat, but you okay. Elizabeth Castellano, and thank you. So, all right, good. So let's go for our break, 15-minute break. 11 o'clock right now, break, 11 to 11:15. Okay. Any questions? Any more questions? There is none. There is none. So let's take a little break here, and we start again in 15 minutes. See you soon. And I have to share the screen as well. Someone is trying to come in, and let's go screen. Okay, and let's start with the first lab. Okay, let's see how I did the assignment here. I want to give you enough time to work on this assignment. When it's due? It's due on the 26th. You have 1 week to work in this assignment, and we are going to do most of the work online. And then you have to do the adjustments there at home and then submit it to me. Okay, let's do that. And I also want to test, right? If I can get your spreadsheet with some little modifications there here in Canvas. I think it works because we did something like that, and I want to try it again. Okay, and let's talk about the lab. See the syllabus. want to get my notes, my lab notes here. Let's see. Okay. So it's right in here. That's the notes for the lab. This lab is specifically about the electric field. Go ahead, download your spreadsheet to your computer. That's posted there in the assignment. So here you go. Lab number 1. I'm gonna put a break here, page break. Insert, page break. Okay, lab 1, electric field of a parallel plate capacitor. Let's put it this way, uniform electric field, okay? Uniform electric field. We didn't cover uniform electric field, but this lab is going to give you the idea how we can come up with a uniform electric field. So far, we covered only point charge distributions, but not a uniform electric field distribution. That is more than a point charge distribution. It's actually a continuous charge distribution, okay? Uniform electric field. Uniform electric field. The question is, how do you get a uniform electric field distribution? Uniform electric field. That's the idea. How do we get a uniform electric field, right? So far, we have covered only point charges distributions. However, in order to get a uniform electric field, we need more than a point charge distribution. Okay? We need a continuous charge distribution. And that I'm going to emphasize continuous here for you. Okay? What is a continuous charge distribution? A continuous charge distribution is an almost infinite number of point charges very close to each other, okay? That's what a continuous charge distribution is all about. You have, by the same token that you have different point charge distributions that you can create, you also have different continuous charge distribution that you can create, okay? And what's a continuous charge distribution? Continuous charge distribution is a bunch, the large number of electric charges very close by each other. Very close by each other. Okay? Continuous charge distribution. And let me see if I'm gonna get a slide here. Let's see if I have a slide. I want to have a picture of this continuous charge distribution so you can visualize it better. Illustrations. Continuous charge. Okay, right in here. Right in here. Okay. So here you go. If you have that's a generic drawing of an object, of a large object, okay, that I managed to charge it. And this object is actually made of several point charges that are very close to each other. Okay. And if you want to calculate the electric field of this huge object, not just a single point charge, but several point charges in there, you have to account for the electric field contribution of each part of the object. This part here, this point here in the object is going to contribute an electric field that's going to be pointing along this vector direction, right? Here you go. Here you go. If the charge is positive, the electric field contribution of this small section of this object is going to be in this direction. Now, if you, and then you have to sum up the contribution of every point of this object. For instance, this delta Q2 charge distribution will contribute another electric field that's going to be something like that, and so on. Okay, here you go, another one, delta Q3. Okay, and then what you do, you sum all those vector fields and you get the net vector field. Okay, that's the idea of a continuous charge distribution. For today's lab, we are going to do a continuous charge distribution that shows up very frequently. Is the uniform charge distribution. Let me get that here for you. Okay, a uniform charge distribution. Okay, right in here. Okay, it's like a plate. If you go ahead and put a bunch of positive charges here in this object, and they are uniformly distributed throughout the here, what do we have here? The charge is greater than 0. And if this plate is large enough, what's going to happen? You will create a uniform field distribution on the right and on the left. What do I mean by uniform charge distribution? A uniform field distribution. I mean that the electric field strength at this point is going to be equal to the electric field magnitude at this point, the electric field magnitude equal at this point, and so on. And they will all be pointing in the same direction. Okay? On the right side, the field will be to the right. On the left side, the field will be uniform to the left. Only this bulk of the region here, okay? At the edges, is going to deviate a little bit. Okay? Can you remember that easily? Okay, if you have a negative plate like this one, the field will also be uniform, but it will point towards the plate. Okay, so here you go. Let's document that in our lab. Not this one. Okay, so far we have covered only point charge distributions. Point charge distributions. However, to get a uniform electric field, we need more than a point charge distribution. We need a continuous charge distribution, which is a very large number of charges packed together and very close to each other. Okay? A continuous charge distribution is almost an infinite number of point charges very close to each other. This is just another way of writing that up, okay? Now, to create a uniform electric field, and that can be proven mathematically, to have a planar distribution of electric charges that are uniformly, you need a planar distribution of electric charges that are uniformly distributed throughout it. Okay, so if you were to picture the charge distribution here, how would it look like? Let's see if I have an illustration here for you. Doesn't look like we have it. I'm going to have to write that down here for you. You know, so in this specific case, okay, because we have a positive charge distribution in this plate. So basically we have something like that. Okay, positive charges distributed all over this plate. Don't forget that this plate is a two-dimensional surface. I am illustrating it only as a one-dimensional surface, but in reality is going to be something like that. Can you picture that? Okay. Another way of illustrating this charge distribution, let's see, I'm going to erase all of that, would be just to draw a plate like that, planar plate, blue color, right? And fill it up with, now I'm looking from the top right of the plate. Fill it up with positive charges, like that. Okay, like that. Like that, like that, like that, like that. It goes like that. Huh? Thank God we have computers nowadays, because doing this thing by hand would have been a nightmare. And now I'm going to fill this whole plate with positive charges. Can you picture that? It's not just 1, 2, or 3, or 4, but it's actually an infinite number, an almost infinite number of charges. We are talking about the Avogadro number here. By infinite, what do I mean by infinite? I mean the Avogadro number right here. And then, and now I put too many charges here. Can you memorize that? Okay. If you have this type of distribution of charges, and it has to be uniform. What do I mean by, so it's not just a uniform field, it's also a uniform charge distribution. And what do we mean by uniform charge distribution? It means that the density of charges here must be the same density of charges here, must be the same density of charges here. This must be the same density all over this two-dimensional plate. That's what we mean by uniform charge distribution, okay? So, and I'm going to clarify here in the notes. Okay, so to get a uniform field distribution, and uniform field distribution means, you know, the field has the same direction and magnitude all over the place. You need the following. 1, a planar surface. 2, a uniform charge distribution throughout this planar surface. Okay? And uniform charge distribution means uniform charge distribution means what? You know, the density of charges in one position in the plate is the same density at another position on the plate, right? On the plate, not in the plate, it's on the plate, right? And it is possible to do that, okay? It is possible to do that. And that's what we exactly do in the experiments that we performed at LA Harbor, actual experiments, right? Here we cannot perform actual experiments. We can only perform a make-believe experiment. You have to rely on your imagination how we do that. Did you get the idea? Okay. And the illustration of my planar distribution is right in here. If we look it sideways, it looks like that. And the field is pointing to the right on the right side, to the left on the left side, whenever the charge distribution is positive. If the charge distribution is negative, then it's all the way around. Okay? Now, what we usually do in the lab, we don't work just with one plate. We just don't work with one plate. What do? We actually combine one positive plate with the negative plate. Okay? That's what we do. The amount of charge, the density of the number of charges that we have here is going to be the same number of charges that we have here. The only difference that we are going to have an excess of electrons here, and we're going to have an excess of protons here. That's the only difference. And when we combine those two plates, you can go back to what we see right in here, right? What we have right here, what you're going to have. The field of the positive plate is going to superimpose with the field of the negative plate. Okay? In all those three regions that we have, in between the plates, they superimpose, and outside the plate, they're going to superimpose. And something interesting happens when we do that, when we combine those two plates. Within this volume, the field of the positive plate reinforces the field of the negative plate. But outside this volume, the field of the positive plate cancels out with the field of the negative plate in both cases, in both sides. And what you end up having is something like that. The fields are being they're summing up, right? And outside this volume, you get an electric field that is equal to 0. Can you remember that? So now we have two different distributions of charge. We have the point charge distribution, both positive and negative. And now we have the planar charge distribution that generates a uniform electric field. Okay, there are more, but we start with those. This uniform electric field is its counterpart, its mechanical counterpart, is the gravitational field nearby the surface of the Earth. Okay. Did you get the idea? That's what this lab today is all about. Okay. We are going to work with something like that. We're going to simulate a uniform electric charge distribution that will create a uniform electric field distribution. And how do we do that? There is a very smart way of doing that. Let's see if I need to write down any more things here. Okay, here we go. A planar surface, a uniform charge distribution throughout this planar surface. Uniform charge distribution means the density of charges in one position on the plate is the same density at another position on the plate. Okay. When we combine two planar charge distribution that is positively charged with another planar charge distribution that is negatively charged, you get a uniform charge distribution between the plate, uniform, not charge distribution, sorry, uniform field distribution between the plates, and a 0 electric field outside this volume. And a zero electric field outside this volume. That's what I'm documenting here. How do you create something like that in real life? How do you create something like that in real life? Well, that's what the answer is going to come, right? The answer is going to come next. Well, the answer is going to come next. And I prepared this slide here for you. The first thing that we do, we use like what people call a conductivity paper. I like to call it resistivity paper. It's sold out there. Those things are mass manufactured. Okay. Answer, right? Let's go back here. We use a conductivity paper. I prefer to call it a resistivity paper. Let's take a look at the internet. Those conductivity papers are sold out there. They have this black color. Okay, conductivity paper for the electric field lab. Okay, let's see. I want to see where we buy those things. Let's see where we buy those. Pasco sell them. And let's see, electric field mapping. Let's see, where are the paper? Advanced placement. They don't have a picture here, but they have a picture there in the other one. Let's go back. Unfortunately, physics sign in. Huh. Oh, here you go. Right in here. It's right in here. Okay, that's how the paper looks like. It's a black paper. A black paper with a X and Y Cartesian coordinate system. Okay, and each. Let's see if I can get larger here so you can see better the paper. Yeah, can I zoom in? Yeah, I can zoom in. Do you see that? The site uses cookie. Oh, yeah, okay. That's how the paper looks like. It's has a coordinate system. Each distance here that you see here is 1 centimeter. Okay. 1 centimeter, 1 centimeter in this direction, 1 centimeter in this direction. You see that conductive paper? They call it conductive paper. Let me fix that in my conductive paper. Resistive. I prefer to call it resistive paper. When you call it conductive paper, gives the impression that the paper is just like a metal, but which is not true. That has zero resistance, which is not true. That's why I don't like it. The name conductive paper. And that's what I illustrated right here in my PowerPoint. Okay. And how do we simulate? How do we create a parallel plate configuration of electric charge? There's a way to do that. Right, so conductive paper. This paper has a black color and is sold out there. Okay, so we start putting together our list of equipment, right? Equipment and materials. 1, conductive paper. Conductive, and I'm gonna insist it here, resistive paper. I need to get some water. My throat is complaining. Yo. And then what else do we do to this paper? We have to modify to create our parallel plate configuration, comma, we have to modify this conductive paper. And we modify this conductive paper by using a metallic paint. Metallic paint, okay? A pen with a metallic ink. Let's not use paint. Let's call it ink, metallic ink, which is the same as a metallic paint. Metallic ink with pieces of nickel dissolved throughout it. Okay? And can be silver too, okay? You know, there are some metallic inks out there that they also put silver, nickel or silver. So pen with a metallic ink. And we get our pen with that metallic ink, and then what we do? We paint our parallel plate writing here. We can do that. Think about drawing a line which is just our plate seen sideways. Okay, you have to think that this line is sticking out from your paper. That's how you have to think in terms of this configuration that you see right in here. Each of those drawings here that you see, we call it the electrode. Why do we call it an electrode? Because it's made of metallic shards. Okay, you have metallic shards here either of nickel or silver, and you have metallic shards here either of silver and nickel. Because it had this paint is rich in metals, this surface that you end up drawing here becomes far more conductive than this surface, this black surface that you see here. Far more conductive. Charges end up moving more freely in this region than in this region right in here. This paper behaves much like as a dielectric, not exactly, okay? Behaves much like as a dielectric compared to this electrode. Compared, okay? So the electrode is far more conductive than the paper itself. Okay, I'm gonna write that down that for you. Now, the importance of understanding, right? The two types of different electrical materials, conductive and dielectric. Conductive and insulators, right? Okay, so we draw an electrode in our conductive paper with our metallic ink. This metallic ink has a conductivity that far exceeds the conductivity of the paper. The ink, in other words, the ink is a much better conductor than the paper. That's what it means. Okay, and again, to simulate our uniform planar distribution of charges, we draw this line here that represents my parallel plate seen sideways. Okay? And then there's more. There is more we have to do. What else do? We go ahead and place this paper, this resistive paper, conductive paper, on the top of the cork board. Don't forget, the cork is a material that is a very good insulator. Okay, so going back to the draw to the, here you go. Now chat. I don't want to chat with you. Here you go. Okay, so do you see the cork board here? That's the kit. Okay, here's the cork board here. We can buy this cork board. And by the way, here is the metallic ink, metallic pen. Okay, is oh, see here. This one is silver. They put shards of silver, not shards, but silver powder in the ink. Conductive silver ink pen. This thing, I believe it costs around $40. Let's take a look. Conductive pen, right? For circuit boards. Yeah, we use that in circuit boards as well. Electronic circuit, let's see. Okay, here's one similar to what you saw there. That's in Portuguese. That's written in Portuguese. This one is $10 only. I thought it was more expensive than that. Okay, silver conductive pen. Okay, bronze pen. Okay, this one is $16 only. Not $16, even 16 Brazilian dollars, right? 16 Brazilian dollars, you divide by 6, you get $3. I'm surprised that's so inexpensive. I remember buying those things for like $40. And they don't last very long, by the way. They last 6 months. So if you're gonna buy it, make sure you use it, otherwise you're gonna lose it. Conductive pen, Amazon. Okay? Different conductive pen. Okay? So they sell that out there as well. And let's write down the cork board. Conductive. We need a dielectric board to place our pen, to place our paper, resistive paper, cork board as a support for the resistive paper. Remember, the cork board is a very good dielectric. We do not want electric charges moving into the supports. That's why we use the cork board. We don't want the cork board also to behave like something that's going to create an electric field itself. Going back here, place resistive conductive paper on the top of the cork board. That's the insert 4 pins to the edge of the paper to secure it on the cork board. We want that this paper to be fixed in the cork board. It doesn't move around. Okay, so that's what we do. We put those pins at the edge. The pins can be metallic pins. Okay, it's okay to have metallic pins, provided the metallic pins stay at the edge here, and at the edge they are not going to interfere with the field that is going to be formed right in here between those plates. So let's write that down. We do not need 4 pins. We're going to need 6 pins, okay? 4 pins to fix the resistive paper on the cork board surface. Okay, next. We are going through the whole procedure. Okay, and I'm trying to make it as simple as possible so you can understand how the whole thing works. Ideally, we should be doing that in the lab, and no, and it works. And this is an experiment that works very well, by the way. Then what we do? Insert one metallic pin anywhere along the left electrode region, okay, and along the other electrode region. We're going to need that, and there is a reason for that. You're going to see, okay, two more metallic pins for those 4 pins. They don't need to be metallic, okay? Those 4 pins they don't need to be, but those two they need to be 2 metallic pins on the surface of each electrode. One metallic pin on the surface of one electrode, another metallic pin on the surface of the other electrode. Let's put that one metallic pin on the surface of one electrode, and another metallic pin inserted on the surface of the other electrode for a total of 2 metallic pins. 4 pins, either metallic or dielectric, either plastic or metallic. So we are going through the step by step. I did this experiment several times. I like to do this experiment, and I already have it, memorize it every step. Next, what we're going to do that right now. Those 2 electrodes here, they are not electrically charged. Right now, those 2 electrodes, they have a neutral charge, and equipment and materials. Let's see. You know what? 4 pins. The metallic. I'm going to do the following. Here's the procedure, right? Conductive procedure. Here's going to be our procedure, experimental procedure. We have to modify this conductive paper, and we modify it by using a metallic ink, the species of nickel, silver, powdery, right? Powder of nickel and silver dissolves throughout it. We draw an electrode in our conductive paper with our metallic pin. Has conductivity far exceeds the conductivity of the paper. This ink is a much better conductor than the paper. Okay, fix the paper on the surface of the cork board with 4 pins placed at the edge, right? It has to be placed at the edge of the paper. Insert one along the electrode. 1 pin on one electrode, another pin on the other. Each electrode, right? Each electrode. Insert 1 metallic pin anywhere along each electrode. That's the procedure. Let me get rid of the cork board. I don't need that, right? Because I already spelled that out. 4 pins, either plastic or metallic. Don't need that. 1 metallic, 2 metallic pins. 2 metallic pins. I'm just making a list of my experimental apparatus that I'm doing here. And then right now, here you go. Right now, your conductive paper has a 0 electric, is no, not has a 0. Conductive paper is electrically neutral. Electrically neutral. We're almost there for our break, right? We now need to charge it. Okay, that's the next step. If you're going to produce an electric field, you must have some electric charge. Okay, so let me see that I'm missing here some of your questions. What do the black arrows represent? Black arrows, where black arrows, Valerie? Any of the drawings you're mentioning? Let's see. Help me out here, Valerie. She asked us this question. Let's see. The black arrows in the drawing from the plates. In this here, or in the other one, or in this here. This one here, right? It must be this one here, right? Okay, good. Yeah, the black arrows means the electric fields. Remember, we represent electric fields with an arrow. Okay, just like we represent force with an arrow, everything that's a vector quantity, vectorial quantity, we represent by an arrow. Okay, did you get the idea now? Okay, so why do they go to the, oh, they go to the left because this plate here is positively charged, right? Do you see the positive charge here? That's why they go to the left. If I were to invert the polarity, if I were to make this one positive and this one negative, then the arrows would point to the right. Make sense? The electric field lines, remember the electric field lines, they start at the positive charge and they end at the negative charge, right? Positive charges are source of electric field, negative charges are sink of electric field. That's why they are pointing in this direction. Make sense now? Does it make sense now? Okay, so let me see, someone is trying to get here. Okay, good. And let's see, when you show the slide, do the pins have to be directly across from each other? Are you in the drawing from the plate? Are you talking about these pins here or those two pins here? Okay, those two pins, yeah, those pins can be anywhere. Okay, anywhere in the surface. This guy can be here, can be here, can be here. Okay, and they don't have to be directly across each other. No, they don't have, provided they are in that electrode. Okay, provided they are in the surface of that electrode, making contact, physical contact with the electrode surface. Okay, doesn't have to be directly in front of each other. No, it doesn't. Okay, can be anywhere. And now we are going to charge those electrodes. And we charge the electrodes by using a power supply. A power supply is nothing more than a battery. It's a fancy battery, right? It's a battery that you can adjust the voltage. So let's go add that to our list of things to do, right? To do our list of equipment. Let's see, fan, metallic, battery, power supply, not battery, but power supply, adjustable power supply, 10-volt power supply. Let's put that like that. 10-volt power. Now, adjustable power supply. Let's put it this way, adjustable power supply. Okay, and then we're going to do here, set your power supply to 10 volts. when we set the power supply to 10 volts, now we get to connect the negative of the power supply to one of those electrodes. Okay, and the negative side of the power supply is usually indicated by a black color. Let's take a look at the power supply out there in the internet. Maybe they have it here. Let's see if they have a power supply here. Oh yeah, the power supply here. They sell on Pasco cells. Okay, they have all sorts of power supply. This one go all the way up to 18 volts. Okay, and you can adjust the voltage. If you're going to use 10 volts, you adjust this one of those knobs until 0 to 18 volts. See that? Until you get 10 volts here. DC power supply. Do you see here? You have the red color. They put here a blue color. Usually the negative is black. I do not know why they put a blue color here in this negative here. The blue color, the red color represents the negative of a power supply. The red color represents the positive of a power supply. You can look at other power supplies out there, power supply, anyway, to see power supply. Okay, see this power supply here? They put the negative as the black color, right? The green color one is the ground of the power supply. We don't usually use in those experiments. And the red color is the positive. So much that they put a positive sign here. Rejoining, okay. Going back here. So now you choose which one is going to be the negative electrode, which one is going to be the positive electrode, right? I chose the left electrode to be the negative one. I am connecting the negative side of the power supply, the negative polarity of the power supply, to this left electrode. Okay, and in order to connect, we are going to need 2 cables. We're going to need 2 cables. So let's add that to the list of equipment. Adjustable power supply. Let's see. 1 black cable with an alligator connector and 1 red cable also with an alligator. With an alligator connector. Okay. And let's go back to Pasco website. They should show us the the kit. The kit with the cables right here. Here you go. Red and black. And why do you use that? To connect the power supply to the electrode, to the pinned electrode. Okay? That's what this cable is all about. So when we do that, now this plate will be negatively charged. There is a cable, a black cable going to the negative connector of the power supply. And then you do the same to the other one, but it's going to be with the positive. And now those 2 plates are charged. Just by connecting them to the positive and negative side of the power supply, you get to charge them. I can do that even with a battery, okay? Here you go, my battery here. Right? Let me right in here, my battery. I'm going to stop sharing momentarily. Remind me to turn on the sharing again so you can see my battery more closely. If I connect a cable copper cable to this positive side of the battery, and then I connect it to a metal plate. The metal plate is going to be positively charged. I get a second metal plate and connect the second metal plate to the negative pole of the battery, and the other plate is going to be negatively charged, negative and positive. Okay, that's what we are doing, but we are doing that with a power supply. Going back to the sharing mode. Let's see, here we go. Now we have an electric charge here. And at this very moment, the moment that we have a charge distribution right in here, the charges are uniformly distributed because you have a metallic surface, a very good conductor. The moment that we charge those plates, you're going to have an invisible electric field between those two electrodes. And the electric field is going to be a uniform electric field. And we are going to map this electric field. There is a procedure to do that. What time is that? 12:08. Okay, in order to do this mapping, you have to visualize an x-axis along this paper. We need a coordinate axis, Cartesian coordinate axis. And we are going to need a y-axis as well. I usually tell my students to get the midpoint of these two electrodes. Here is going to be the 0, the origin of the axis. Okay. And, visualize a line connecting those two, the two tops of the electrodes. I tell my students not to draw those lines in the paper. Don't draw it, because you're going to damage the paper and your experiment is going to be a disaster. But just to visualize it, and then we are about to start the experiment. Okay, we are about to start. The second experiment is going to be just like that, but with a different configuration, okay? Before we start the experiment, I want to take a break. We have 1 more minute to go. Let me write down here in my notes, right? Let's see, power to 10 volts. Connect one electrode to the negative pole, right, of the power supply. Use the black cable. Connect the other electrode to the positive. Connect the other electrode to the positive pole of the power supply. Use the red cable, 1210. Okay, your electrodes are now charged. And let's go for a break. 12:10. We are almost there to start the experiment. Break from 12:10 to 12:25 p.m. We are going to be here until 12:50, right? Let's see here. Notes right in here. Yeah, we're going to be here until 12:50. And then I see you in 15 minutes. Okay. I will stop sharing. I will pause. I am back here. And we are almost done with the experiment. We're setting it up, setting the conditions to perform our measurements. We didn't start our measurement yet. And we have one more instrument that I have to introduce to you. It's a multimeter, a digital multimeter. We need that. Okay, there are all sorts of digital multimeters out there. I have one right in here. Here you go. That's one type of digital multimeter that you're going to see out there. They have all sorts of shapes and forms. Okay, it has a screen to show to you. What does it do? What does digital multimeter does? It measures voltage, measures current, and other things as well. Okay. So let's add that to our list of equipment. Digital multimeter. One. Digital multimeter. DMM to measure the voltage throughout the resistive paper. And here you go. You set the multimeter. Here you go. Set your DMM to read voltage. Okay, set your DMM to read voltage. That's one thing that you have to do. And then you're going to need another 2 cables again. You're going to need 2 cables again. Two cables again. One black and another red. That will be connected to the DMM. Okay, to be used in the DMM. Connect, here you go. So what you're going to do here, connect the second black cable to the negative of the from, not to, right? From the negative of the multimeter. Connect one end of the second black cable in the negative of the multimeter, from the negative mode of the multimeter to the negative of the electrode. Okay. The multimeter also has a positive and negative terminals. Here's another example of multimeter. See that? You have a connector here, black and red. Here's the negative connector of the multimeter. Here's the positive. So you're going to get a black cable, connect to this black terminal, to the electrode of your paper. Okay. And then we do something else. We connect the red cable to this red jack and just leave it hanging there. Don't connect the other end to anything else. Okay? That's the difference. That's the important difference between the positive of the multimeter and the positive of the battery. And there's a reason for that. Connect one end of the second of a black cable. Of another black cable, right from the negative of the multimeter to the negative of the electrode. Connect the other red cable to the positive terminal of the DMM and leave the other end of the cable hanging. It's not a cable, it's like it's more like a probe. Okay, let me, instead of connect the, okay, so let me see, no, it's not two cables, right? It's one, not a, one black cable, and a red probe. Okay, the probe is just like a cable, and a red probe that will be connected to the multimeter. Connect the other red cable to the positive terminal to connect the red probe to the positive terminal of the MM, and leave the other end of the cable hanging for now. It's going to be this probe here that's going to do the measurements. That's why he needs to be hanging there for now. That's the reason. And now let's go back to our, okay, so try to visualize now. Okay, we have the power supply. Let's see if I have another drawing of that. I'll have to figure out a different drawing for you. Let's see. Or maybe it's just better to see a video, right? Let's see if you have a good video there in YouTube so you can have a better idea how this thing is set up. Okay, so let's see. Equipotential lines.
In this experiment, you'll be measuring the G.
Okay, do you see the paper here, the black paper? Here's the cork, right? And here's my electrodes. One electrode, another electrode, right? One electrode and another electrode. See the multimeter right in here? Right, we have a battery here, and this one looks like, yeah, these one are the cables that are gonna charge those electrodes. Okay, this guy here is supposed to be connected to this pin here. The black one is already connected. And what I mean about probe is exactly what you see right in here. It's like a pointed device. Here you go. I have the probe of my multimeter right here in my hand, but it broke, you know. Unfortunately, it broke. Here's the cable, right? That goes right in here. That's how it looks like. It's something like that. This end goes to the multimeter, and this other end here is used to make measurements. And let's see how this one goes. Let's see.
Geometry and magnitude. The electric field set up in a sheet of mildly conductive paper by connecting a 9-volt battery to different
9-volt battery. See that he's not using a power supply. He's using a 9-volt battery, and he has a battery here, which is okay. It should work as well.
Conductive ink painted onto the paper. You'll do this by using a multimeter to measure voltage drops in the paper and find sets of equipotential points in order to draw lines of constant potential from which you can determine the electric field. Consider the electric field of a single charged particle. The field lines point directly away from the particle in all directions. The potential increases as you get closer to the charged particle, but it doesn't change if you move along concentric circles around the particle. These lines of constant potential are always perpendicular to the electric field lines.
Okay, here you
To
go.
find the equipotential.
See that, the paper, the electrodes. When I perform this experiment, I usually draw the electrodes in this direction here. That's how I prefer to use, but he decided to use it this way. And do you see how the battery is connected to those electrodes? At this very moment, this electrode here is positively charged, and this other electrode is negatively charged. The battery is right in here. The 9-volt battery is right in here. Okay, the battery is physically connected to those electrodes. You have to be touching it. And look at the probe here. the red probe and the black probe. In this experiment, we don't need the black probe. In this experiment, all we need is a cable without the probe. But the red probe, we are going to need it. The cork board, everything that I mentioned to you.
Lines in your conductive paper. First, connect the 9-volt battery to each side of your conductive pattern. Set the multimeter to measure voltage. Place one of the probes on one side of the conductive pattern and leave it there. Touch the other probe to a spot on the paper and record the voltage and position.
Okay, that's exactly how we do. We get the negative probe at rest right here, fixed at this negative position. For this reason that it doesn't need to be a probe. It can be a regular paper, can be a regular cable with a alligator connector there to keep it here. What's gonna move along and make the measurement is gonna be this red probe here. Okay, let's see if it shows how to do that.
Move the second probe and find another point that has the same voltage. Continue until you found enough points to make a closed circle or a line that goes off the edges of the paper. Next, move the second probe until you find a different voltage and repeat the process. Find enough equipotential lines so that you can fill in the space between the two sides of the pattern. You can draw your points
he
and
doesn't
record
have
the
it,
voltages on a
unfortunately.
piece of graph paper, or record them in a spreadsheet and use this to
Okay,
plot
so
the
let's stop
equipotential.
here. This guy doesn't show the procedure, the measurement procedure, unfortunately. Let's see if this one shows.
Sua empresa fatura a partir de 20 mil. Você
skip
quer
it.
lucrar ainda mais? Conheça a Infinity Pay, a máquina.
Hi, everyone. Thanks for looking at this electricity lab. You're going to be drawing electric field lines for this lab. You're going to need a clear plastic container, a 9-volt battery, a voltmeter, 2 nails, some water, 2 graphing paper, some tape, and 2 alligator clips. What you're going to be doing for this lab is you're going to be drawing electric field lines. So we're going to have graphing paper that's numbered on the x-axis and the y-axis. Once you number it, you're going to put that graphing paper underneath the clear container.
Yeah, this guy is doing it different. Let us skip it. Let's look at another one. I don't like the way he's doing. It's not the way we do it, but I'm quite sure it works. Let's see. This one maybe is better. Let's see.
Okay, so here's the experiment. We're going to, it's called a field mapping experiment. We're actually going to map out electric fields, and we have to do a little bit of theory.
Take a look here. That's the power supply. See that? Can you recognize that? And here is the multimeter. This one looks like better one. And here's the black paper. You can see the electrode. Most likely the other electrode is hidden right now.
After this to show you.
Okay, here you go.
So
right in here, the electrode, right? He put the electrode too close to each other. I don't like to work with electrodes so close to each other because you don't have enough space, you know, to get enough data.
Basis of organic chemistry. In any case,
let's see. I want to show you how they make the measurements with the multimeter, so you can have you know, the. Let's go, man. Okay, he's connecting.
Field set up by these wires.
He's connecting the battery to those 2 electrodes to charge the electrode, and I want to show you how he performed the measurement. Okay, here you go. The red probe the red probe is is loose, right? And the black probe from the multimeter can be placed either here or it can be placed here in the power supply as well. He decided to connect to the power supply because this point here in the power supply is exactly the same as this point here in electrically speaking, all right? This point here in the conductor. Well, 40, we have 10 more minutes to go. Okay, I'm gonna give you 1 more week to, we couldn't finish it, this one, but we continue next time. But let's do as much as we can today. Here you go.
Call it 0. Okay. So on this end, it's a little bit not quite 0.
It's too bad. His hand is in the way. Okay, that's not a good video. He should be careful when he was doing this video. That's a problem of being able to making a video so easily, right? You forget some small important details.
Sure.
See, basically what he's doing, he has put that pointer, that probe, somewhere between those two plates to take a measurement. And the multimeter is indicating here the voltage, okay? Multimeter is indicating here the voltage.
That's pretty much zero. everywhere.
Okay.
Okay, so this is called the 0-volt line, and this is the 6-volt line. And we found equal potential lines because
And by the way, I can see from this experiment, he is making some important mistakes that I don't make in my lab, okay? One important mistake that he made here is this spin. This pin is not at the surface of the spin. Those two pins, by the way, is not completely in the surface of the electrode. This electrode is too thin for the spin to be completely in touch with it. Because of this problem, you don't get very good measurements, okay? And I could see from the measurement that he got, instead of getting at 0 volts, he was getting 0.14 volts, okay? So unfortunately, this guy didn't do as good a job
and over on this.
that he could have done. Let's take a look at another, let's see. Maybe here.
Line up in someplace.
Yeah. Okay. Now he's measuring, but again, his hand is in the way. What a shame, you know. He seems, what a shame. You cannot see the probe moving from this plate to the other one, but that's exactly what he's doing. Okay, the red probe. And let's see if he has anything else. Okay. I will continue with my own slides. I hope you had an idea, a better idea. And here you go. So now we have, we are going to make sure everything is working as advertised. We're going to get the red probe of the multimeter, and we're going to touch the red probe right in here in this metal pin to make sure that he reads exactly what he's supposed to read. This is just a test to make sure that everything is working fine, okay? If your multimeter is touching this surface anywhere, doesn't have to touch the pin, can touch this surface too, metallic surface anywhere, it is supposed to read 10 volts because this guy is set at 0 volts and this one is set at 10 volts, okay? So that's a test that we do. And touch the red probe anywhere along the surface of the left electrode, read your voltage. Now you're doing another test to make sure everything is working fine, and you're supposed to read 0 volts here. Red probe of multimeter here first, 10 volts. Red probe of the multimeter here, 0 volts. Red probe anywhere within this region, you should be anywhere, anything below, between 0 and 10 volts. Okay, and now touch the red probe to the pin of the red electrode, read your voltage. Okay, we already did that, right? Let's see. Okay, now we're going to start collecting our data. Let's see, we have 6 more minutes to go. Okay. So what we're going to do, you're going to find a place between this negative plate and the positive plate that is equal to 1 volt. But if you look at those points along this line to make it, your data well organized. Okay, and that's how I found out how to do the experiment in a very well organized way. Look along this line where you have 1 volt. Okay, the red probe of the multimeter is placed here. Look for this 1 volt. Write down the 1 volt and write down the X and Y coordinate system. Y should be 0, X should be whatever. And that's exactly what you have in your spreadsheet, okay? 5 more minutes to go. And then here I'm just explaining, all this explanation that I'm providing you is going to be good for the next, the next lab, the lab number 2 that we're gonna do should be here, raw data, okay? Lab number 1, I'm gonna get, go, no, I don't want that. I want the other one. I want this one right in here. Yeah. Okay, good. Good. So here is the data that we already have, okay? I didn't do 1 vote. I started 2 votes. Sorry for the misunderstanding here. Okay, so this guy here, so I can write down 2 votes here instead. And that's going to be, you know, the X position and the Y position. See that the Y position is 0. The Y position is 0 because we are looking at 2 volts along that line, along the X line. Then we are going to do not just for 2 volts. Okay. Record the X and Y coordinates in your spreadsheet. Okay. Touch the red probe of the left and read your, let's see, what am I doing here? Okay, for some reason I got the wrong. Okay, 2 volts. 2 volts, right? You know what? I'm gonna leave 1 vote, okay, for now. Otherwise, it's gonna be too much work, and we are going to lose time. Okay, so just think of that as being 2 volts. Okay, and now find 3 volts along this horizontal line. 5 volts, 7 volts, 9 volts. Your spreadsheet may be slightly different. So now I found a place where I have those volts, and I will need to get other points that has 1 volt, 3 volts, 5 volts, 7 volts, and 9 volts. Okay, the next thing I do, I look for those values of 1 volt along this line. That's how I do. I like to organize the experiment in this way. It shows, you know, it gives us a very good base to proceed, okay? And then 1 volt here, 3 volts here, 5, 7, and 9 volts. And that should be, you know, going back to your spreadsheet, should be one of those points right in here, should be this one here, okay? That's the further away from the axis. Should be those ones right in here. Now we are no longer probing, making measurements along the x-axis, right? We start making measurements along the x-axis. Now we're making measurements along the edge of the plate. And then everything else in between. Everything else in between, okay? 2 more minutes to go. I'm gonna finish with this. And now, you know, everything else in between. And then 1 more here at the top, okay? Outside this region. You're going to see the electric field is not going to be uniform in this region. The electric field is uniform only within this region here between the plates. Outside, the electric field is no longer uniform because you're escaping from the edges of the charge distribution, okay? 1 volt, 3 volt, 5, 7, and 9, okay? And then you fill it up the rest. A total of 6 points per volt. 1, 2, 3, 4, 5, 6. And, okay, you should get something like that. Because it is a uniform field, uniform electric field, you should get this voltage distribution that almost parallel to each other. Only at the edges they start to deviate, okay? And that's how you get, okay? And we'll talk more about that next time. We're going to go through all your spreadsheets. The spreadsheet is not due next week. Okay, I'm gonna postpone it to the other week. And next week on Wednesday, we work out on that again, okay? Any questions about that? It was a very long explanation, right? But this explanation is gonna be good for the next lab that we're gonna have as well. Okay, so 12:50. If you don't have any questions, we can finish right now, and I'll have my office hours right now. Okay? You two have a good weekend. Thank you.
Bye, Professor.
Goodbye.
Thank you. See you next week.
See you next week.
Hey, Professor,
Professor.
are you gonna,
See you.
are you gonna contact the bookstore still for me?
Yeah, I will. I will call them. I'll send them an email and try to resolve your problem. And you already talked to LA Pierce, right? You told me, right?
Yes, Yes, we just have to get it. Yeah, Pierce, library, they know. So
Uh-huh.
yeah, you guys got to.
Not the library, that's the bookstore, right? It's not the
Yeah, the
library, right?
bookstore. Sorry about
Yeah, yeah. Okay, thank you. Okay, I'll send them an email.
that. Thank you.
Thank you. Bye-bye. And don't forget to send the email, okay? Because I need to know the details. You said that you get money from EOPS, right? That's what you get money from?
Yes.
Okay, so put that in your email, the name of the program, and let's see how we can resolve that.
Okay, I'll email you right now.
Okay, thanks.
Hello?
Yes? Who's
I was
that?
wondering if you can compare this slide to the Excel sheet because I was a little bit confused when I was reading the values.
Okay, so you want to compare what, the voltage values, or what's exactly you
Well,
want to do?
how might this slide compare to the values on the
Okay. How this slide here, the color one compares the spreadsheet, right?
Yes.
Okay, so let's I'm gonna put them side by side, okay? So let's see here. Okay, and now let's get the spreadsheet right here, okay? But the numbers are different, okay? I put 1 here, okay, and I put 2 here. So let's say, you know, all those points all those points along this line here, you can see that y is equal to 0, right? Do you have that like that in your spreadsheet?
Yes.
Okay, which group are you there? What spreadsheet group number is that?
I think
That you have?
group 3 or group 4.
Okay, do you have that in front of you in your computer?
Yeah, I have it open.
You have open. Can you read it so I can pick it up here so I can show you exactly what you have in there?
Where would you like me to read it from?
I just want to know the name of the file. This
Oh, the
file
name
here.
of the file. It
Yeah.
says group 3 on my file.
Okay, so let's get the number 3. So everything is exactly what you have in there. Number 3. Okay, and get this guy right in here. Oops. And now, okay, so you can see that all those measurements, first measurement, they're all y equal to 0, right? Y equal to 0, right? Do you see that in our spreadsheet?
Yeah.
Okay, is that large enough for you to see or too small?
You're good. I have
Okay,
it
good.
open on my laptop too, so.
Okay. So all those data that you see here in this first, in this line, okay, correspond to those data points here
Okay.
along this X line, okay, because it's y equal to 0, okay?
Yeah.
And then next, let's see. Let's see, this one here, 4, 2, 2, 3, 1, 2, 9, 2. Yeah, okay. This one here, measurement number 5, okay, correspond to this line here at the top, okay?
Oh, the dash line.
Yeah, the dash line, okay? And this one that has the highest y value, right, correspond to lines outside the dash line. See that?
Yeah, I see.
Okay, and everything else is those 1, 2, 3, 3, right? Yeah. I have how many measurements? 1, 2, 3, 4, 5, 6. Yeah, that's right. Everything else is those 3 points here. Okay, that's how you relate the drawing that you see here to your spreadsheet. Make sense now?
Yes, it does.
Okay. And
Thank you.
I'm going to explain that better next time, right? Right now, I just want you to have a qualitative idea what we're doing. When we go back next Wednesday, I'll tell everybody else about those points.
Okay. Thank you
Okay.
for the clarification.
Okay. Welcome. 5 minutos. Tuesday and Thursday. 5, 6, sai 2 horas e 5 minutos. Zero, meia. 3, 4, 9, 0, meia, 2, 3, 4. Yes. Isso, eu recordo do português. Não, vou desistir do vídeo. Which lab section do you have in mind? We're working. Section do you have in mind? One more question. One more question. Don't we have to request to an office of the college? This to file the documents. college, abuse, type of situation. Daniel Keller. Dan Keller. Ah, it's the dean. Ah. Everything was typical skin is a solution. Solution plant. What about what about what about 130? What about the building? Above Friday, 1:30 p.m. So proposed policies of salt. Against students. Good. And you can see that the mason is you Permission number. Permission number. AM. Well, 60 AM. Volume. And once. Equal to the class records. Once you register. You that's all the canvas. Yes. Has Yes. Option. Yes, 18, não. Pois. Yes. Either way. Whoa. Oh, quarter. The one. I presume it meant. I presume it meant the. I presume it meant it's 28. Maybe. Maybe. Agreement, have agreement series. It's 38. No. No. 2, 1. Oh. Wow. What do you think? Okay. Okay, so it's okay. Yeah, number. Oh shit. Annette, oh caramba. Physics 38. Nicholas. Criação. Então,
18h30.
ah, sim. Obrigado. Obrigado, estamos. Isso. Isso, isso. O Rafael já chegou, né?
Já.
Foi ontem, agora não me retornou ainda.
Ah, meu bem, quer saber de uma? O Rafael já tá aqui. Uhum. Eu já falei, já mandei mensagem para ele hoje. Eu falei para ele nos priorizar, porque nós já vamos pagar aluguel e ainda nem estamos morando lá. O aluguel cheio que eu falei o mês todo. Ele, deixa eu ver aqui. Deixa eu ver minha mensagem. Vai. Uma mensagem de 1 minuto para ele, então eu vou ouvir direito para o que eu falei para ele.
Aham. Acho 904. Isso aí. Não pode sofrer. Ou simplesmente.
Aqui. Eu pedi para ele priorizar o nosso. Falei que nós não tínhamos mudado ainda, quando tinha que instalar a energia fase lá 220, tinha que instalar o ar-condicionado.
Sim.
Aí eu pedi para ele nos priorizar também, colocar na lista de prioridade, e aí as outras coisas ele. Como é que eu falo? Para ele priorizar esse assunto.
Sim. E aí, o que ele disse?
E aí, ele só falou assim, ué, também pode deixar. Mas ele não falou que...
Que ia vir amanhã, né?
Não, deixa eu ver aqui. Falou que vai priorizar, mas não falou do jeito que
Não falou, olha, senhor Francisco. Não, mas vai demorar para eles se estabelecerem aqui agora. Ai, gente do céu. Nunca aconteceu isso comigo, meu amor.
nem comigo. Vamos, quando for amanhã, você pergunta para ele se ele pode vir, assim, numa emergência aqui para instalar o ar-condicionado.
Tá. Amanhã, né? Espera até amanhã.
Uhum.
Tá bom. Tudo bem. Vai para um outro país, fica um mês, depois volta. Vai para outro país morar, fica um mês, e depois volta.
Ainda bem que ele veio com coisa para fazer.
É.
Ele vai receber dinheiro, porque eles fizeram um investimento alto. Aí a Angélica falou que ela não queria, para não brigar e não ficar um para um lado e um para o outro, ela